This is the fourth part of my lecture on probability distributions, in which I'm going to be talking about the normal distribution. The normal distribution was discovered by Carl Friedrich Gauss. He was a German mathematician and physicist, possibly the greatest mathematician since Newton's time. As a child he was a mathematical prodigy, and there is a story that at the age of 10 his school class was asked to add the numbers from 1 to 100, possibly as a punishment. Gauss immediately wrote down the correct answer, which is 5050, while the rest of his classmates struggled on for an hour but still didn't manage to get it right. There is, of course, a trick to how he managed to do it so quickly, but it's amazing that Gauss had discovered that at such an early age. At age 15 he studied at university in Braunschweig, and then at age 18 in Göttingen. And at age 30 he became Professor of Astronomy at the Göttingen Observatory. He's well known for many contributions to mathematics and physics and astronomy, but in the field of statistics he is responsible for introducing the normal distribution in 1809 in connection with his work on least squares minimization. So the normal distribution is also known as the Gaussian distribution in honour of Carl Gauss. It's a continuous distribution, unlike the discrete distributions of the binomial and the Poisson distribution we've looked at so far. So as a continuous distribution it can take on any value, not just whole numbers, and the numbers can be positive or negative. However, it is always symmetric about the mean, unlike the other distributions that we've looked at so far. The variance of the normal distribution can be chosen independently of the mean. For the two distributions that we've looked at so far, the binomial and the Poisson, the variance was dependent on the mean. But for the normal distribution we can choose the variance to be any value regardless of what the mean is. However, if we choose to set the variance equal to the mean, then the normal distribution becomes a good approximation to the Poisson distribution, as long as the mean is more than about 10. Because we know that for a large mean the Poisson distribution becomes symmetric, and for the Poisson distribution its variance is always equal to the mean, so we can get a close simulation of the Poisson distribution by taking a normal distribution and setting the variance equal to the mean. The normal distribution is important because many real observations approximate to a normal distribution, but the variance isn't necessarily equal to the mean. It can be any value at all in real life. If you want to simulate the normal distribution in Excel, there is a function called normdisp that does just that. Here are some examples of some normal distributions. The red curves shows a normal distribution with a mean of 0. Notice that it's symmetric, so the mean is equal to the mode in the middle of the distribution, and a standard deviation of 4 that tells us the width of the distribution from one side to the other. Here in green is another distribution with the same width. It's got the same standard deviation of 4, but this time it's got a mean of 70. Illustrating how we can independently change the mean and the standard deviation. Here in blue is another normal distribution. This one has got a mean of 50 and a smaller standard deviation of 2. Because the standard deviation is smaller, the height has to be greater, because remember the area under all of these curves must add up to a probability of 1. So of necessity, reducing the standard deviation narrows the distribution, and that has to increase the height in order to keep the area equal to 1. So the purple distribution has got the same mean as the blue one of 50, but its standard deviation is quite a bit larger. The standard deviation of 10 means this distribution is much wider, and consequently, to keep the same area, it isn't as tall as the blue one. So you can see we can get a great variety of normal distributions to suit all our needs. Because of such a variety, it's difficult to tabulate values, and so we can standardize it in a particular way. If we have a quantity x, something that we're measuring, which is distributed according to a normal distribution with mean m and standard deviation s, like the example curves that we've just looked at, then we can define a new quantity, x minus m divided by s, and it turns out that that quantity will be distributed according to a normal distribution with a mean of 0 and a standard deviation of 1. That's important, and we call it a standardized normal distribution. So the standardized normal distribution has a mean that is defined to be 0 and a standard deviation that's defined to be 1. That makes it easy for calculation because we can tabulate the values. But in general, our normal distribution doesn't have a mean of 0 and a standard deviation of 1. So if we take this normal distribution shown in purple here with a mean m and standard deviation s, what we can do is to first of all shift it to the left so that the mean becomes 0. That's what the x minus m in this quantity does. It shifts it by subtracting m from all the values and moves it to the left so that the mean is 0. Then if we divide by s, that squashes it down into a taller and narrower distribution where the standard deviation becomes 1. That converts our normal distribution into the standardized normal distribution. So in practice, whenever we end up with a normal distribution with an arbitrary mean and arbitrary s, we will typically convert it into this standardized form by subtracting the mean from all the values and then dividing by the standard deviation to convert it to this standardized form, the standardized normal distribution. And in many books, when people talk about the normal distribution, they mean the standardized normal distribution on the assumption that it's been converted to this standardized form. And certainly if you look it up in tables, you will find it in this standardized form. This is the shape of the standardized normal distribution. As we've said, it is defined to have a mean of 0 and a width or a standard deviation of 1. So the horizontal axis is not in terms of our actual measured quantity, but in terms of how many standard deviations we are away from the mean. So going to the right, we go 1, 2, 3 or 4 standard deviations away from the mean, and to the left, -1, -2, -3, -4 standard deviations. Excel has a function for calculating this called norm sdist. Notice the s in this function for the standardized normal distribution. The important thing about this is that the shape is well defined, and if we go from 1 standard deviation below the mean to 1 standard deviation above the mean, then it covers 68% of the area under that curve. In other words, if we choose a value at random, 68% of our measurements will be within that yellow shaded area, within plus or minus 1 standard deviation either side of the mean, from 1 standard deviation below the mean to 1 standard deviation above the mean. In other words, it covers 68% of the area under the curve, because the area under the curve covers 100% of all measurements. So 2/3 of our measurements, or just over 2/3, fall within 1 standard deviation either side of the mean. Even more important is what happens if we go 2 standard deviations either side of the mean. From 2 standard deviations below the mean to 2 standard deviations above the mean covers 95% of all measurements. In other words, 95% of the area under that curve is contained in the purple and the yellow areas. The area from 2 standard deviations below to 2 standard deviations above contains 95% of all the possible measurements. In other words, the little tails at the bottom and the top, only contain 5% of the area under the curve, so a measurement chosen at random from this distribution only has a 5% chance of falling in these tails. That's why we call this range from 2 standard deviations below the mean to 2 standard deviations above the mean are 95% confidence limits. If we take a measurement at random, we're 95% certain it will fall within that range showed by the shaded area. If we go even more extreme to 3 standard deviations below the mean to 3 standard deviations above the mean, then we find that 99.7% of all measurements fall within that area. The bits left in the tails below 3 standard deviations below the mean and above 3 standard deviations above the mean is only 0.3%. So this standardized normal distribution is a very handy way of quantifying the distribution. And these facts are worth remembering. For a normal distribution, 68% of measurements lie within plus or minus 1 standard deviation of the mean. More importantly, 95% of measurements lie within plus or minus 2 standard deviations of the mean. Those are called the 95% confidence limits, and we'll meet them several times during these lectures. Going more extreme, 99.7% of measurements lie within plus or minus 3 standard deviations of the mean, which means there's only a 0.3% chance of being in those small tails, and 99.994% of all measurements lie within plus or minus 4 standard deviations of the mean. So there is only a very small probability, 0.006%, of a measurement lying more than 4 standard deviations above or below the mean. Notice I've quoted these for a normal distribution rather than for a standardized normal distribution, but the results are always true for any normal distribution as long as we express them in terms of how many standard deviations we are away from the mean. Now, there is a law of large numbers, which in common English is called the law of averages, although in common use it's very often misunderstood. This law is in fact developed by Jacob Bernoulli, who we've already heard about in connection with the binomial distribution. The law of large numbers says that the average proportion of successes from a number of Bernoulli trials will tend towards the expected proportion as the number of trials increases. That may seem a bit complicated, but let's think of an example. If you're betting on roulette and you bet on the red, then what we're saying is that on average the proportion of wins, the fraction of time that you win when you bet on a red, approaches the expected value, which is 18 out of 37 after a large number of bets. It doesn't say that you will definitely win 18 out of 37 times exactly. It says that if you go on betting for many times, an average over many trials, on average the fraction of wins will be 18 out of 37. In fact, that's how the casino make their money, because it means that 19 out of 37 times you lose and the casino wins, which means they win slightly more than you do. It does not mean that after a losing streak the ball's more likely to land on a red next time. So if you've had 5 blacks in a row, it's no good betting on red thinking that the law of averages says that it must be red next time. That's the gambler's fallacy. The ball has no idea that it's just had several blacks and it's due for a red. All it will happen is that on average, over many bets, the red will come up 18 out of 37 times. And even then it only gives you the fraction, not the actual number. The actual discrepancy between reds and blacks gets more and more as the number of trials goes on. It's only the proportion that tends to that. Anyway, that's a bit of a digression into betting, which is not really what we're supposed to be talking about. Let's get back to its relevance to statistics, and the central limit theorem is important to our discussion. Because leading on from that law of large numbers, the central limit theorem says that the sum, or the average, because the average is after all just the sum divided by the number, so the sum of a large number of independent random variables will be approximately normally distributed. That means they follow a normal distribution. Now the surprising thing about that is that it's true even if the distribution of each variable is not normal. So the central limit theorem is important because it says that the normal distribution crops up even in circumstances in which the binomial distribution or the Poisson distribution or some other arbitrary distribution is underlying. In fact, many real observations are due to a sum of many unobserved random events. That's why the normal distribution crops up so often in real measurements, because the central limit theorem says that the normal distribution will come up as the average of lots of other distributions. So the normal distribution is in fact the most important probability distribution in statistics. The trouble is, it's only accurate for large samples because it says in the limit of a large number of measurements. But as long as we're dealing with a large number of measurements, the normal distribution occurs very commonly. Here are some examples of the central limit theorem showing how the normal distribution comes to be important. We've already looked at the example of the number of bone scans we did each day in the nuclear medicine department, and we already saw in this example that it was not normally distributed. It was in fact quite a skewed distribution. So we can't say that bone scans every day is normally distributed, but if instead we add up all the days in a month to give the total bone scans every month, and we look at the distribution of that from one month to another, then what we're doing is adding up several of these bone scan distributions, and the central limits theorem says that that will be approximately normally distributed. So over many months we would expect to find the number of bone scans done in a month to be normally distributed. Here's another example based on patient's height. Patient's height may or may not be normally distributed, I don't know. But if we take a group of 100 patients and work out their average height, and then take a different group of 100 patients and work out their average height, and so on, if we take lots of groups of 100 patients and plot a distribution of the average height of each group, the average height of all the groups will be normally distributed, because the central limit theorem says that averaging lots of groups like that, the distribution tends towards the normal distribution. Intelligence is another example, because a person's intelligence is actually a result of many unseen genetic and environmental interactions. It's something that we can't deliberate exactly how it comes about, but because of all those random distributions all averaging out, it turns out that IQ is normally distributed. So, as we see, the normal distribution is very important in statistics. So that's the end of the fourth part of my talk on probability distributions. In the next part we'll look at the student's t-distribution.